In
And
action.
it's really 4, not pages 1 through 5. There's page 1, 2, 3, 4 coming out. This is page 2, page 3, and there should be a 4. All right, here's more 3s. Here's a 4. All right. All right, here's another 4. Okay, how are we? So everybody needs 1, 2, 3, 4.
1, 2, 3, 4, 5. And do we want page 1 of 3?
That we're going to do later. All right, it's coming. All right, now, this is our lab. So what you want those people to see, sweetheart,
Yep.
is this angle here and this angle here. Okay?
Okay. So
they want to look at the fact that I have hanging masses here. Actually, you might want to come just sort of show the apparatus where we have this bar. The vibrating distance is from here to here, and we're going to measure that in a minute.
There's a little string right there if you can't see.
Here's a string. And then the string comes down through here,
Here's
and I
E
put
flat.
tension. Can you really tell? All right. All right, and I'm going to put tension on it, and we're going to use this software, which is on the website,
Software.
to see where the resonance frequency is of the string. All right?
All right.
So what they're really going to be reading when we do the experiment is they're going to be looking at this software on the screen. Okay?
Gotcha.
All right? All
Guys
right.
got it?
I got it.
So
Now
where
you
should
wanna- So I think where they
where
want
should
to
we
be,
set up camp?
I think they should be looking at the screen. So I think they need to be looking at that screen. We can move this away if you want.
Gotcha.
All right. Okay, now, prior to Sarah and Alan coming, prior to Annie and Alan coming, Sarah and Ryan measured some things, okay? We took a sample of the fishing line, and that sample was 0.55 grams in mass. So if you convert that into kilograms, you're going to divide by 1,000. So it's 5.5 times 10 to the negative 4. We took it outside just like we did with the spring, and we counted the times. 22.5 feet was the length of our sample. And we know that every 3.28 feet is a meter. We have not calculated, but we need to calculate how long it takes. And then this mu is not the coefficient of friction anymore. This mu is now the mass per unit length. So it's the density. Mass per unit. So mass per
Scoops is
unit
over here.
length. All right? Okay. So if you would first do for me the following favor, and that is if you please calculate that for me. So you know what it is. And for the people absent, we're looking at the lab called Relationship Between Tension in a String and Wave Speed.
Alright, I got them set up looking at that screen right
That's exactly what I want. All right?
Perfecto.
So this is the name of the lab. All right? Which will be linked to Learning Exchange. Which you don't submit online, you write up. Yes?
Yes.
Okay. So we had in our sample, we had a sample that was 0.55 grams in mass, which we converted to kilograms. And we had it 22.5 feet long, which we converted to how many meters? Seven?
Oh, it's 4.26.
That's all it is 4.26?
Did I do that wrong?
3 goes into 22.
I got 6.
I would think it'd be longer than that. How much?
6.8.
This is a 3. Did you
Oh,
do
I
that
thought it
right?
was a 5.
There we go. Okay.
Okay.
So say it again, Sarah.
6.86.
86. All right. So now, if I want what's called the mass per unit length, or the linear mass density, both those terms mean the same thing. the linear mass density, you take the total mass by the length of the string, and we get how many kilograms per meter. And I think scientific notation is the preferred method. Can I erase this data? You got it all, yes.
Yeah,
It's,
you're good. What did you get?
8.0175. Okay, so when you do it in scientific notation, you get
8.02 times 10 to the negative
8.02.
or 1.7, but like, do you have to have,
02 is fine.
okay,
Times 10 to the
10 to the negative fifth.
negative fifth. Okay. Now, on the handout, we're working only with the light string because I couldn't find my heavy string. So I guess that means, although if time permits, we might try it with wire. That would be a totally different event, all right? Okay, so if you look at the diagram, and maybe you all want to come up here and see what this looks like, because I know Ryan got to because he was videoing it, but you might want to see too. All right, so what we have here is, this was tied by Sarah, this nice knot. This is a bridge, and the string is across from here to here. Can you see that? There's elevation here, all right? So the string is constrained here and here. Yes, no? Okay, so that means this is my vibrating segment, okay? We need to measure that vibrating segment. So how long is that vibrating segment in blue that you can't read? Okay, so vibrating
From the center or from the edge?
from this here to that there.
Okay. It is 22.7, no, 8, sorry.
Okay,
Yeah.
good enough. All right, 22.8 centimeters. All right, now, when I pick this in the center, if life is good, and I've finally gotten it working, all right, when I pick this, can you barely see that blue at the bottom?
Yeah.
Okay, and when we turn the lights off, we'll see it a lot better, okay? Now, what that's telling you is the frequency this microphone is picking up, all right? Now, that vibrating segment is fixed at this end and fixed at this end, okay? So that vibrating segment is forming a loop. And that loop is a half of the wavelength,
Yes.
okay? So that means that based on this distance, so that's L. So the length of this is one loop, which is half a wavelength. All right, so therefore the wavelength would be twice this number. Does that make sense? So that would be 0.456 meters. Yes?
Yes.
Now, the microphone is going to tell you the frequencies. Okay? So we're going to keep the same wavelength all the time. So lambda is a constant. You don't have to write it if you don't want to. All right? We're going to use we're going to get different frequencies for different weights, which becomes the tension, because the weights are putting tension in the string. Good? So instead of using weight, can I now replace this with tension? Yes? All right. Now, the wave formula we know is VW equals F lambda. The wave that we're going to create is tension over mass per unit length. Okay?
So we want to get the
So we're going to record the tensions. we know mu, we know the mass per unit length, we know the wavelength, and we're gonna record frequencies, correct? Now, I'm changing the tension by putting different weights on it, correct? So that means we would write the square root of tension over mass per unit length equals F lambda. Agreed? So T over mu is equal to F squared lambda squared. And I think I'm gonna move this down,
Just wanna see this,
22.8.
so, not doing that.
Alright,
Now,
now, I am controlling the tension, correct? If I'm controlling the tension, that means it should be the x-axis. Yes, no?
yes,
And we are reading the frequency, yes?